Hello and welcome to my lab. Today I have this HP OmniBER communication analyzer. I don't even know exactly what it does, but I got it very cheap just for the parts. Probably there's some interesting technology inside, maybe some parts I can reuse, maybe I can reuse the case to make a portable lab computer. In any case, I might just try to turn it on, but if I take this apart it won't be the loss of a very nice instrument because telecommunication has developed so quickly. This thing's really antiquated and it's very specific in its purpose, so I can't really use it for anything else. Now, I think I bought this one as broken. Probably it's not even properly tested because it's hard to get the equipment to properly test it. But let's see if it turns on. It's quite noisy. Well, the display is definitely bad. That's broken. It's very dim and it's the very classical LCD pattern broken thing. If I hook up an external monitor, I see that it doesn't even boot up, regardless of the broken screen. So it really is a dead device. If you look at the side of the unit, you see all the various connections used to test the telecommunication lines. And here, let's see if I can get the handle out of the way. You can see 3 fiber optic connections. And they use the same adapter pieces that HP uses on their other fiber optic devices. And these adapters can be somewhat hard to find. A lot of HP optical stuff gets sold without this small adapter piece. So it's actually very useful that I now have 3 in reserve. So these are for FC fiber connections, and this is the adapter piece that you can screw off. So underneath is just a fiber ferrule that plugs into this adapter piece, and you can get these for all kind of different connections. But a lot of times equipment is sold without these and with just this bare connector. Now this is the optical interface. Here is a multi-rate analyzer for, I guess, is it 52 and 155 megabytes per second or megabit. It is 75 ohm connections, clock, trigger. I guess this is for some telecommunication standard I don't really know. A clock, a transmit, a receive module. 10 megabit Ethernet. So if 10 megabit Ethernet was the standard at that time, then a 155 megabit communication link really would have been quite fast at that time. It has last been checked in 2012. Now there's a 1310 nanometer and a 1550 nanometer laser in here, so it might be interesting to salvage these parts. So let's take it apart. I guess the case comes off if I unscrew it here. But of course, with devices like this, it's always a nice puzzle how to open them. You can hear and feel a lot of these fingers around the device. Of course, you don't want any interference on a device that's used to measure the error rate of your communication, because if this thing itself can introduce errors, you really don't know what you're measuring. So this instrument itself should be really noise free and really quite quiet on the RF parts. Caution, metric and inch hardware, consult service manual. Oh, that's going to be interesting. So one layer down, you can see that a lot of modules are bridged by, I guess, some RF link for clock out and data out. And there's a note here: modules should only be removed or inserted by trained personnel. Well, I guess I'll consider myself trained at the moment. So let's have a look at the modules one by one and see what we can find. So there are a lot of different coax cables running around this board. This is a fiber cable that comes in. This top is a fiber optic receiver module made by BPC, good for 1200 to 1600 nanometers. On this side of the board is one very big heat-sinked chip, some unpopulated connections, here in between we can see the two laser modules. The yellow things are the fibers coming out, and here are the RF signals going in. Probably there's a connection on the back side as well, and this will be the high frequency link that will modulate the laser diode current. Now at the back we have a many pin connector that will go to a backplane in the module. Of course, now it's interesting what's inside the box. Let's have a quick look. Looking inside the box, we see a very big chip, and there was a pad on top that connected it thermally to the top lid of the box. But for the rest, a lot of electronics, I guess some calibration potentiometers, all marked with red paint, so that they, if you adjust them, you'll see they have been changed. And the receiver itself is this small box here on the top left. So all in all, maybe I can use this receiver, but all of this is probably very much complicated, maybe even custom-made components. You can see the loosened name of the chip has made its way onto the thermal material instead of staying on the chip. And there are 4 coax cables running out. I guess they provide the data lines or signal that this detector can measure. Let's see if I can take it further apart. You can see a gold outline here. Maybe this was meant at some points to have a shielded can on it, but it wasn't installed. So either it was not necessary, or this board is used in different designs, or some other reasons. And you can see by the traces and how the components are laid out quite spacious, that this board is not designed to be as compact as possible, but to really route the signals as is needed for the high frequency. There's a voltage regulator here, a bunch of status LEDs for the different voltage lines. And this is an LM337T. Ah. This is the board with the 2 lasers. Let's see if I can separate them. This is one of the 2 laser boards. This one is the 1310 nanometers, plus minus 20 nanometer. So these are the 2 laser modules. Let's open one up and see what we find inside. So inside the laser module you can see here the laser diode itself in a butterfly package. The fiber is routed around a few times before it goes into the sleeve there. And it looks like a lot of analog and electronics actually. Although it will be very difficult to figure out how this all is made. It's quite a full populated PCB. So chances are that I'll just salvage the laser diode out of it. And probably I won't put in the effort to see if I can understand all this. Especially if there are some custom ICs in here, then I don't think I have any chance of getting this driver to work. If you look at the connection here, that's I don't know, like 20 pins on the back side. So it's quite a complex driver, and of course with no part number or documentation, I guess the best I can get out of this is the laser diode. And even for the laser diode, I hope that there's a datasheet available for the pinout. Otherwise I might just open up the lid and see what's inside there. With the optics done, let's continue to the other modules. Well, look at that. Let's have a closer look at the digital boards. So this is the multi-rate analyzer, and you can see it has quite some impressive heat sinks on here. So I guess these are really the workhorses of the device, and you can see all the pathing on the PCB. Looks like it's made really for high frequency. You see some loosened chips. Here again the ceramic packages with something soldered on top. You see they use two separate boards, perhaps because this board is made more for, I don't know, analog RF stuff. And here you can see a lot of Xilinx chips, so I guess this is the digital portion of the board. And all the communication that goes a bit further than you can do with traces is done via these coax cables. That's pretty neat. You can see they put quite some effort into the design of this device. You can even see a potentiometer there. The RX clock adjust. Here's a TX clock adjust trigger. And everything's nicely clearly labeled, test points. And these kind of expensive limited run measurement machines, you often see test points because, well, there's not a lot of them made, and if you have to, because they're so expensive, they're worthwhile to diagnose. Now on the back of the board you don't see a lot. The Xilinx chip, I guess some bus interface chips, but otherwise it's a pretty empty board. And also if I take a peek in between, looks like there's a lot of digital stuff on the back side of this board, but otherwise there's not much going on in between the boards. Interesting packages over here. And this board has some nice RF stuff going on with two cans. This is the clock board, and I've already taken the lids off these aluminum cans, but there's not a lot of stuff going on in here. This is a VCO screen, I guess. PD screen or PU, hard to read. And there's a Qualcomm chip on here. They do a lot of communication stuff. Another quartz oscillator. Xilinx chip with, I guess, another bus interface ICs. And this looks like it's a power transistor for high frequencies. And otherwise, not a lot of interesting stuff to see here. Some voltage regulators. So that was the clock board. This is the transmit board. You can see it's much more aimed at digital electronics. There's a lot of Xilinx stuff going on here. Some quartz crystals. I guess this is just power supply stuff. And here are a lot of these blocks with the Matsushita brand. So I guess these are relays or maybe even attenuators for the signal. Since they're so close to the front end, I'd almost think that they're attenuators. But you can also here see an LM337T voltage regulator, so I don't know, maybe it's something else. Well, the back of the board is also quite populated. So this is a lot more digital electronics. Which of course for a digital communications test set makes a lot of sense. This is the receive board. You can see it as a... It looks quite similar to the transmit board. There's a lot of digital logic here at the back. But at the front it's slightly different. Here we see a gold outline. I guess at some point this could have been made into a tin can, but I guess they found it wasn't necessary. Again, here are the black Matsushita blocks, and having them inside one of those can areas basically, I would assume that they are indeed attenuators and not just run-of-the-mill relays. And at the back again filled with digital electronics. Wow! Now this really is a retro piece of kit. We have 8 megabytes flash memory. That will probably be the operating system. This looks like a CF card. And some RAM here. I guess some Edo RAM it looks like. And this CPU, well, judging by the ceramic package, that's something like, I guess, Pentium 1 style processor package. So just to show how old of a computer is inside this thing in relation to how fast the communication is that it's testing. So you can see that with this old school computer technology, it's a lot slower than a communication bus this was meant to test. So then you need this whole infrastructure just to communicate very accurately and actually measure how you're communicating, and if any errors occur. Because of course for a next gen communication bus you need even the next gen after that metrology to check if the communication is actually going right, or if there are errors, jitter, and those kind of things. So all of that capability then runs off quite a simple CPU. Now if we look inside the chassis, we can see here on the right hand side the power supply and a very big backplane with a lot of those multi-pin connectors, and on the left is the display and its drivers and its connectors. And here you can see the fan that kept the whole thing cool. It's a very big, I guess, tubular style of fan. It moves quite difficult by hand, and it will provide an airflow across all the boards. I wonder how they assembled this thing, because the power supply was very hard to get out. I loosened all accessible screws, and still I had to fiddle with tie wraps and hidden screws just to get the power supply out. Well, it looks like it's a perhaps standard commercial unit mounted in here, plus some HP custom PCB on top of it. And let's see if I can get the backplane out and the display. I got the backplane out, I got the fan out, and I unmounted the display, so then I can take it further apart. On the backplane you can see this very big row of very high density connectors. This really is a lot of pins that's linking it together, because you know, if high clock speeds are difficult, well, you'll have to go parallel. These are the two connections to the power supply, quite a bit. This is also distributed over the backplane, and here the display plugs in. Now this fan is supposed to keep it all cool. One of those interesting tube fans. And this is the display, and well, looking by this sort of crispy connector, I would almost guess there was a short in there somewhere. So let's see if I can take this further apart. Now this PCB must be the high voltage for the lamp, or 2 lamps actually. Considering the display was quite dim, I don't think it was doing quite well. There we go, that's the display. You can see in the right angle of the light, you can see the big crack. Must have hit it. Neck display. Look at this. It seems, if I do this right, let's see if this works. These are the lamps. They slide out of the unit. Here. These are the compact fluorescent lights that run along both sides of the display to illuminate it. Of course, they were not working quite well, but if you look at how easy they can be unmounted for the display and remounted, mounting new lamps into this display would have been quite simple. I've seen a lot of screens where these lamps are just built in and pretty much never replaceable unless you tear the thing apart. These are actually remarkably easy to take out. I took the front panel apart a bit further, and you can see that the crispy cable actually belongs to the buttons on the front panel. So perhaps here there was some kind of short. This plate was behind it. You can see again those aluminum fins also to shield the front of the box to make sure it's completely sealed in terms of electromagnetic interference. And the front panel looks like it's some kind of cast aluminum. It's pretty thick and rigid. That's it for this video. I hope you enjoyed it. I made quite a mess, all the internals are spread out. So I'll see what I can salvage of these, and I'll probably salvage the case of the item, see if I can make a nice device into that. Thanks for watching, I hope you enjoyed, and I hope to catch you next time.